Okay, so most of the properties that we're going to collect from Xbar actually come from either what we call the baby central limit theorem, if you assume that xi's are normally distributed. All right, so this is our first bullet, the baby central limit theorem. Then X bar has a particular normal distribution, or the central limit theorem itself. So I just want to go over quickly our assumptions for the central limit theorem, and then we're going to do sort of a motivating example, which will segue into some of the information that we need to know about X bar in order to start building into a confidence interval. Okay? So remember, the general assumption here is that the xi's are independent and identically distributed, and we sample from a random variable x. Now for the baby central limit theorem, we assume that this x is normally distributed with mean and sigma. But for the general central limit theorem, we just have a random variable. We know its expected value, which we will denote mu. It's quicker than writing expected value every time. Is finite, and its variance, which we'll call sigma squared, so its standard deviation is sigma, is also finite. We define x bar to be the sum of n different independent observations divided by n. And essentially we have three different versions of the central limit theorem. So the first one says if you take this x bar random variable, you subtract mu and divide by sigma over square root of n, then this becomes the standard normal distribution. Okay? Now this is kind of true generally. If you have something that's normally distributed, as we see our x bar is, if you scale it by if you shift it by subtracting the mean and then scale it by dividing by its standard deviation, you always end up with the standard normal distribution. So we proved that all of these things are equivalent. A second version of this would just be that x bar itself has a normal distribution with a mean mu and a standard deviation of sigma over square root of n. The last version of the central limit theorem that we kind of talked about is that if rather than thinking of a group mean, we think of a group total, this you can also write as a normal distribution approximately, and then these are the appropriate parameters. We're primarily today going to be working with version 1 and 2. So let's consider a motivating example. Suppose we have workers employed in a large service industry, and they have on average a wage of $7 per hour with a standard deviation of 50 cents, and let's assume that these wages are normally distributed. The industry has 64 female workers, and these workers have an average wage of $6.85 per hour. So the average across the females in this industry is $6.85 per hour. So the question we want to answer here is it reasonable to assume that the wage rate for women is equivalent to that of a random sample of workers from those employed in the service industry? In other words, we're trying to use probability to figure out if there's a bias against women. Are they making more? Are they making less? Than if you were to just randomly sample 64 people from the service industry, right? So I'm going to jump over to R, and this RMD file should be in your snow day page, so you should be able to access this. And we're going to consider this question. So here's the thought. Same setup. We know that our samples, our xi's, are normally distributed with a mean of 7 and a standard deviation of 50 cents. All right. And using the sort of baby central limit theorem, we know that the sample mean is going to have a very particular mean and standard deviation. So this means the sample mean random variable is normally distributed with a mean also of 7 and a standard deviation equal to 50 cents divided by the square root of our sample size. Now in our case, since there are 64 female workers, we're going to compare this against a random group of size 64. So we're going to divide this by 64. Okay? Now here's the idea. If we consider the group of 64 female workers, we know they have an average wage of $6.85. So let's explore what the probability is for a random collection of 64 people to make $6.85 per hour or less. Okay, so our guess here is that in fact the females are biased and they're underpaid. And so we're going to explore, if we were to just randomly select 64 people from this population of workers, what's the probability that they make the same as the group of females or something less? All right, so in other words, what we're looking at here is the probability that our sample mean random variable is less than or equal to 6.85. Okay? And we can do this very quickly since we know, in particular, the probability distribution of our sample mean random variable. It's normal. It has a mean of 7 and a standard deviation of 0.5 over square root of 64. So we can find this directly. This is already in cumulative form. It's already in a less than or equal to form. So we could just use our p-norm with a 6.85 as our input, right? This is what we're less than or equal to. And now we can use our parameters of 7 and 0.5 over square root of 64. Okay? And we can see that the probability that a randomly selected group of 64 people makes the wage of the women or something less is under 1%, right? So this would indicate that there is a bias against women in this industry when we consider the wages, right? Does this make sense? Now, the question we want to follow up with, and this is sort of moving us more towards the confidence interval, is sort of a follow-up thought, right? Okay, so 685 is an abnormally low wage for a group of 64 people to be making, right? Specifically, it should occur less than 1% of the time if we were randomly selecting 64 people, okay? So this is a very low wage. So let's ask the question, well, if we're just randomly selecting 64 people from the industry, where do the sample means for these possible random collections likely fall? Okay, and this is going to move us towards the idea of a confidence interval. So here's the general idea. We already talked about this. If Xbar is the random variable that models the mean wage for 64 randomly selected members, right? This is a random variable. What values are typically going to be coming out of this random variable? We already know its probability distribution. And so we can kind of set up a picture that looks like this. So here's our random variable X bar. We know that the peak of its distribution is going to be at 7. And let's suppose when we're, let's solidify what we mean by likely falling, right? Where would the sample means likely fall? So let's make this a little bit more specific. And let's say, where would the sample means fall 95% of the time? Okay, so we're going to make this switch. So we're going to label this kind of middle 95%. And notice that it has the highest values in the middle here. It has the highest values for your density curve. So these are going to be the inputs with the most likely, these are going to be the outputs for your random variable that are most likely associated to these highest values for the density curve. All right, so we want to know what's the middle sort of 95% of this sampling distribution, or of this distribution for our X bar. Right? Well, if you have 95% in the middle, and this thing is nice and symmetric about the y equals 7 line here, right? This vertical line at 7. That means we have 5% split up into each of the two tails, the left tail and the right tail. All right? So the question is, we want to find X bar outputs, right? Range values for X bar that sort of mark the beginning of this blue region and the end of this blue region. And we're going to call this the middle 95% for this sample mean random variable. And this 95% of the time is where these sample means should fall as we're taking randomly selected members of size 64 and computing their mean wage. Okay? Does this make sense? So, typically what we can do, we can think of these as percentiles, right? So we could use our Q norm function inside of R to figure out, well, what's the 2.5 percentile? And in this case, the percentile we're considering on the right here would actually be 97.5 because there's 95% and then an additional 2.5% to the left. Okay, so if we want to know where the middle 95% of randomly sampled means would fall, essentially the beginning of that region should be the 2.5th percentile, and the end of that region should be the 97.5th percentile. Okay? So, based on our picture in the slides, the beginning of our, quote, 95% region would be the 2.5th percentile, and the end of the region would be the 97.5th percentile. Okay, so we can jump into R and quickly compute these. We could do Q norm, 0.025 is the percent that we're considering, and we know that the mean is 7 and our standard deviation is 0.5 over square root of 64. And I'm just going to copy these parameters as a group so I can copy and paste them quickly. We also want Q norm 0.975, 7, oh, there we go. And if I run these two commands, I get the beginning and the end of my 95% region. All right, so in other words, 95% of the possible groups of size 64 would have a sample mean wage that falls between 6.8775 and 7.122, let's round off to 5. Okay? And this is really just equivalent to saying that, the probability that our Xbar random variable, overline X, is in between these two values is equal to 95%. And we can double check this by just using a p-norm. So we would do p-norm 7.1225 with our parameters, and we would subtract p-norm 6.8775 with our parameters. And we can double check this. I rounded, so it's not going to be exactly equal to 95%, but it's going to be very close. Okay? So in this case, we know exactly, using our percentile function in R, right, we know exactly how to find the middle 95% region, which is how we're essentially going to describe where these sample means for randomly selected peoples tend to fall. Okay, so 95% of the time they're going to fall in these little intervals, essentially. They're going to fall in the interval between 6.8775 and 7.1225. And the fact that a group of 64 women fell outside of this usual interval, right, at a 6.85, right, it's outside of this usual interval, that sort of provides evidence that maybe this, this group of women are not being treated fairly when it comes to wages.